Okay, I think it's time to restart. So for those who are coming now after lunch, we are at the 2023 IEEE DS Brazil mini colloquium. I am Marcelo Pavanello. I am the organizer of this mini colloquium this year. And for the afternoon session, we have two presentations. The first one is from micro semiconductor devices to the discovery of the black hole in the Milky Way, which is going to be given by Professor Edmundo Gutierrez. And then after the break, the coffee break, we will have the final presentation, which is reliability of metal gate high K CMOS devices, given by Dr. Andreas Kerber from Intel, USA. Okay, so just to put us all in the right place. Well, with no further delay, let me just move to the next presentation, as we are a bit behind the scheduling. So I'm skipping this, and this. And for the afternoon session, I am starting with Professor Edmundo Gutierrez from National Institute for Astrophysics, Optics, and Electronics. The acronym is INAOE from Mexico. And as I did for the other presenters, for the other presenter, I will say a few words about Dr. Edmundo Gutierrez's contributions. So he got his PhD degree in 1993 from Catholic University of Leuven in Belgium, with the thesis entitled Electrical Performance of Submicron CMOS Technologies from 300 Kelvin to 4.2 Kelvin. From 89 to 93, while working for his PhD, served as research assistant in the IMEC in Leuven, Belgium. In 1996, was guest professor at Simon Fraser University in Vancouver, Canada, and also spent 2 months as an invited lecturer at the University of São Paulo in Brazil, where I took the opportunity of meeting him in the first time. In 2000, acted as design manager of the Motorola Mexico Center for Semiconductor Technology. In 2002, was invited lecturer at the Technical University of Vienna in Austria. In 2005, joined Intel Mexico Research Center as technical director, and currently he holds a professor position at the National Institute for Astrophysics, Optics, and Electronics in Puebla, Mexico. Professor Edmundo Gutierrez is IEEE senior member since 2008 and has published over 100 scientific publications in conferences in peer-reviewed in the field of semiconductor device physics, has supervised 5 Master of Science candidates and 10 PhDs, theses, and is author of the book Low Temperature Electronics, Physics, Device Circuits and Applications, published by Academic Press in the year 2000. Professor Edmundo Gutierrez is a member of the Mexico National System of Researchers and technical reviewer for the Mexico National Council for Science and Technology. And he has been also editor from IEEE Transactions on Electron Devices and IEEE Electron Device Letters, right, Edmundo, if I'm not wrong? Yeah, thank you. Well, with that, with no further delay, Edmundo, please, the stage is yours.
Thank you, Marcelo, for the presentation, and thank you for inviting me once again to come into Brazil. It's a beautiful country with beautiful people. So today just want to briefly resume in a few words what is the presentation of this afternoon. It's a kind of dancing at the edges of the universe, because my institute is an institute which is also doing research on astrophysics, optics, and electronics. So by doing research on astrophysics, you think that we are looking at the big objects like the galaxies. But the only way that we can have a look at the galaxies and the stars is by using very small devices of a nanometer and micrometer size. So that's why we are dancing at the edges of the universe. So at one size, we are looking at the big objects. At the other scale of the universe, we're using very small devices made of many times of semiconductor materials, but sometimes of superconductive materials. So so today I'm going to talk about this, a brief introduction. Probably you are thinking why there is a relationship between semiconductors and the Milky Way. So I want to mention that probably you heard about the black hole in the Milky Way. In May last year, there was an international announcement made by 8 different sites in the world about the discovery of the black hole in the Milky Way. So there were 8 radio telescopes in the world that were working together in order to build up the image of a black hole. The black hole itself is something that we cannot see with the eye, with the naked eyes. It's something that we need to build, because the black hole is eating everything. A black hole is something that is also eating the light, so we cannot see it. So special devices are required in order to see a black hole, and those devices are made of semiconductor devices and superconductor devices. So that is going to talk, that is part of my presentation of this afternoon. So it's really amazing that if you want to see something which is quite far away from our planet, you need to use very small devices. Otherwise, you cannot see the universe. Perhaps you can see the universe if you use optical telescopes, but you are missing important parts of the universe. So the origin of the universe is coming from this radiation, the radio radiation. So this is a picture of the black hole, and as I already said, it was imaged using 8 radio telescopes, and basically by building a network of 8 radio telescopes, you are building a virtual telescope which is the size of the Earth. So that's what you need to detect radiation coming from a black hole. And you may see some specification there. So the Milky Way is, as you may read there, is 26 million kilometers in diameter. It's pretty huge. 26 million kilometers in diameter, and is 1,600 light years away from Earth. So what we are building now with this extremely complex devices is something which already existed many, many years ago. And it's really amazing. We have one of those 8 radio telescopes located in Mexico. It's a 50-meter diameter radio telescope. Is the largest radio telescope of a single dish, and is located in Puebla State, the same state where the institute is located in Mexico. So, as I already mentioned, to have the chance to look at the black hole, we need to use very small devices. In this case, I'm showing the picture of one of the bolometers that we use for detecting some of the first images that we saw with this radio telescope. And what is amazing is that we built some of those devices in our lab. So you don't need any complex or any modern silicon fabrication facility. This is the one that we have in Mexico is a 0.8 micron CMOS technology. So we can build these bolometers and make an array of bolometers and use the system in order to detect light coming from abroad. I have some notes here, so let me open my iPad just to be sure. So this is the first image of the supermassive black hole at the center of the Milky Way. So we announced this discovery. So we are not discovering the black hole. So we are building an image. That is something that you can see with your naked eyes. So it's based on a mathematical model. So we collect information and we reproduce the image that you see there. As I already mentioned, so this is part of the large project that is called the Event Horizon Telescope, collaboration using observation from a radio telescope located in different parts of the world. The black hole is 27,000 light years away from Earth, and it was imaged with an array of 8 radio telescopes that form a virtual radio telescope, which is the size of the Earth. These are the 8 radio telescopes. One is in, 2 of them are in Chile, the ALMA and the APEX. Then there is one in Germany, another one in Hawaii. There is the one in Mexico, another one in Hawaii, and then we have another one in Arizona and one at the South Pole. Those 8 radio telescopes form this very large virtual radio telescope. And you can imagine, so we are collecting information all the time. So the black hole image was built by collecting information since the year 2019. So it took almost 4 years to collect all that information and send the information to a central hub. And so there is a large supercomputing system that is processing all that information using the mathematical models and building up the image of the black hole. So that was really a scientific collaboration of these are more than 700 scientists and students involved in this project. And it took almost, as I already mentioned, almost 4 years to collect and process all that information. So the question is, what is behind the radio telescope? Deep inside of the technology in this radio telescope, you will see that it is amazing. So there is not only the semiconductor detectors or the superconductive detectors, there is also the electronics, the instrumentation. And you can imagine moving this, so having these radio telescopes, you have to control the telescopes in order to follow the stars. So this radio telescope is moving all the time, focusing to the stars that we want to work on it. So it's working the whole time. So we are collecting all this information, and for that you need to synchronize the 8 radio telescopes. So we are using a special clock, which is synchronizing the 8 radio telescopes and collecting the information in a continuous way. So this is really an amazing system. Sorry. So this is what we have. And this is a picture of the radio telescope that we have in Mexico. As I already mentioned, it's a 50-meter diameter radio telescope. And then there is a, let me see if I can point this. So there is a secondary mirror here. This is the primary mirror, which is a 50-meter diameter. Then we have a movement. So the radio telescope is moving like this, and it's also rotating. So we have in the order of 180 individual surface segments, which are placed here. They are controlled. All the time they are being controlled in order to keep a resolution of, in this case, 70 micron, the roughness of the surface is controlled by these 180 different panels. And this is a picture of the secondary mirror. These are the students and the collaborators from USA that were installing this secondary mirror here. So this is 50-meter radio telescope. So you can imagine that working in that conditions is not easy, because so people has to go inside of the radio telescope. There is a elevator inside, so you go to this point and then you work here in order to install this secondary mirror. So this is the Mexico country. So the Puebla state is located somewhere in the center of the country. And this is the mountain where we have the radio telescope is 4,600 meters above sea level. The telescope is located somewhere here. This is the tallest mountain in Mexico. Is called the Citlaltépetl. That's Citlaltépetl is a local language, which we call Nahuatl. It means the mountain of the start. And so we have also the electronics and the optics facilities in our institution. So so we are using this 0.8 micron CMOS facility in order to build up the sensors, the bolometers, some of them. And we also have the optics shop where we are able to build, in this case, optical devices. And sometimes we are also developing the mirrors that we use for the infrared detectors. We are also developing those optical devices in our optics shop. And as I already mentioned, it's a 180 segments radio telescope. Each segment is 5 by 2 meters with 8 composite panels. So this is the material that we use for building these panels. And there are 5 concentric rings around this the radio telescope. So we have an active surface with 720 actuators, which are continuously upgrading the position and the resolution down to 70 micron at the surface. And this is a picture of the radio telescope. So this is one of the single panels which was moved with one with this system here, and is replacing. This is a picture when we were replacing one of the segments. You see the segment here. And this is one of the first instruments that we built together in collaboration with the University of Massachusetts and people from United Kingdom. This is called the Aztec Astronomical Thermal Emission Camera. And this is a picture of the instrument inside of the instrumentation room. This is a cryostat. And this is a picture of the 144 pixel bolometer. It's a focal plane array operating at 2 different bands, 1.1 and 2.1 millimeter. It's operated at 250 millikelvin, and this is a silicon wafer, SOI wafer. I think this is a 4 inches wafer, and this is the array of the bolometers, and this is placed in a frame. So we take that frame down to 250 millikelvin, and this is the heart of the system. So this is one way to collect the radiation coming from the universe, so that we use that information as a part of the whole information of the Air Radio Telescope in order to build up the black hole image. As you may see, it seems to be a very simple. So, but behind that, there is also the instruments that are reading out the information from the array. So they are processing the information, they are storing the information, and they are sending that information to a central hub in Massachusetts. Massachusetts is collecting the information from the other 7 radio telescopes, and they are working with the processing system, and they are building the image by using these 8 radio telescopes, which are interconnected all the time. And this is one of the first pictures that we collected with this system. It's amazing, as you may see. So this is the one of the galaxies that we are working on, and this is the spectrum. And it's really interesting because we are just detecting the presence of different molecules at the universe. So these are the different molecules that we can detect as a part of the radiation that we are detecting from the universe. So this helps understanding the chemistry and physics behind the formation and evolution of the galaxies. So that's really amazing, because in that way you can understand how the universe is being created and is evolving just by using this array of bolometers. Of course, there is a large and complex theory behind that. So in order to understand how the chemistry and the physics is evolving in the universe, you can understand the origin of the universe. So that's why when talking to, I'm not an astronomer, but if you talk to one astronomer, you will see that that's fascinating, because they are talking about the origin of the universe. But if you want to talk about the origin of the universe, you need to have these small devices in order to detect the radiation that is coming from the galaxies and the stars. Okay, this is the just a diagram of how the cryostat. So Marcelo was asking me a few minutes before starting this conference what a cryostat is built. So this is a 3 stages a cryostat. Is a cryostat that is operating at down to 250 millikelvin. And basically, so we put the sensor here. So it's basically a material which is sensitive to the radiation. This is a bolometer. So it has an absorber layer on top and a thermistor. So we have the absorber layer in order to capture most of the radiation. So we transmit that radiation to the thermistor, and then we convert the radiation into heat. So by changing the temperature, so we are changing the current, and that's the way that we are detecting the radiation. So radiation is converted to temperature, and temperature to voltage or current. And we are also capable of putting a feed horn, so we can filter the frequency. So we can select the frequency. So by selecting the frequency, so we are able to detect radiation at different wavelengths. And that was the way that we detected the presence of different chemical components. So for instance, this one here is 351 microelectron volts, 459 microelectron volts. So we just put a filter on top of the bolometer, so we are able to select different wavelengths, and then we can process that and then define what chemical composition is the one that is radiating out from the universe. And of course, this is not an easy task. So you can imagine that there might be a lot of noise coming from the instruments and the radio telescope. So we need to use a very complex instrumentation in order to reduce or filter the noise coming from the system, and also from the radio telescope, because the radio telescope is moving. So there is a mechanical movement which is inducing noise into the system. So we have many filters and systems that are controlling that, so we can detect radiation coming from these chemical components. So at the end, so it is a matter of materials and device structure. So if we are able to control the way the electrons in the lattice of the materials are organized, so we can control the electronic properties. So by controlling the electronic properties and the device structure, so we are able to design and build this. In this case, it's a simple bolometer. So radiation is coming to this plate here, this layer, and that is converted into temperature and voltage or current. So we can in our lab we can design different materials with different detectivity just by using different alloys, not only silicon but also using germanium and other kind of components here. So we can also adjust the wavelength at which we want to detect the radiation coming from the universe. Just as an example, this tells you how long it took to build and put the Aztec instrumentation in play. So we started, let me see if I can read it here. This is 2008. So I can see it from here. It was almost 4 years to start from scratch, designing the instrument and putting the instrument into place. So we have the reflector surface, the optics, the commissioning when people from UK and US came to our place and put the system into operation. Here we have the names of different instruments, the Redshift, Aztec, Sequoia, Speed, and this one, 1 millimeter CIS. This system, 1 millimeter CIS, is the one that we use to build part of the black hole that was discovered in the Milky Way. This one here. All these instruments were part of the radio telescope when we were collecting information for building the black hole in the Milky Way, the image. Okay, there are other instruments like the Speed I already mentioned it, and Sequoia. Here you may see these pictures here, and this is quite similar to the cryostat Adam was showing this morning. Remember the previous talk on the superconductors and superconductivity and quantum computers. This is the kind of cryostat that we use for these systems. Here, this is the Sequoia system. And the question is, what about the black hole in the Milky Way? Let's move. This is the distribution of the 8 radio telescopes. This is the one in Mexico. This is the large millimeter telescope, LMT. And these are the 8 different radio telescopes located in different places on the Earth. And you may see this is the virtual radio or diameter of the radio telescope, the virtual radio telescope, which has been used to build the image of the black hole. And this is the instrumentation. It's quite complex. So we have the radio telescope here. Then we have the receiver. So we separate the information in 2 different bands, and then we have all these analog and digital systems which are processing the information. So we take all that information to storage, and then we transmit the information by using different channels. Sometimes, because of the radio telescopes are located in remote regions, we don't have immediate connection. So we stored the information in special drives, which are closed in vacuum, and then we send the storage system via either by car or any other system. But those are a special storage system that we use in those places. But in our case, in our radio telescope, we have fiber optical connection. So we can send information through fiber optics to Puebla City, and then from Puebla City to Massachusetts or UK for further processing of this information. And well, that's a test description of what is inside of this system. As I already mentioned, we have an hydrogen masers used to preserve the phase against atmospheric fluctuation. So we use a universal clock, which is synchronizing the 8 radio telescopes. And so we are also using the technical specifications are here. As I already mentioned, correlation and calibration is done in USA and Germany, running on clusters of more than 1,000 compute cores at each site. So that's why I was asking this morning, Adam, the option to get access to the supercomputing system so we can process this information in a faster and more reliable way. And this is the another system. This is what we call the MOSCAT, Mexico UK Submillimeter Camera for Astronomy. That's a new system that we just installed in the radio telescope. This is a description of the instrument. So we have a series of optical devices which are reflecting the information that is coming from the antenna. So we process this with different filters, and then we send the information to the cryostat. So we have the sensor array here. So we process all that information and we send it to the storage on the computers. So this is the whole system, the way it's operating. And this is a diagram of the instrumentation room. Is a room which is about 10 by 10 meters, and all the systems are located just behind, under the antenna. There is a building here below, and we have this. As I already mentioned, this system is located at 4,600 meters above sea level. So one of the issues at that place is that there is not enough oxygen. So you need to wear masks sometimes. And so bolometers are not good enough. So we need another kind of devices in order to be more sensible. And those are what we call the kinetic inductance detectors. Those are based on superconductive materials. So in this case, we don't need an absorption layer. So the information is just coming into the superconductive material, which is a strip of a superconductive material. When the radiation is coming, is changing the inductance of the wire, and by changing the inductance of the wire, we are changing the phase and the frequency of the system. So it's a very simple RLC system. So if the radiation is changing the conductivity of the inductance, then the frequency, the resonance frequency and the phase is changing. And by detecting that change in frequency resonance, we are detecting the radiation that is coming from any galaxy or star. And the sensitivity is quite high in this case. And well, this is a description of the system. So this is a fit line, which is inductance. So when radiation is coming, so this is changing the inductance here, and then we are changing the frequency at which this system is oscillating. And then, so current is flowing through this line, and by changing the current, which is flowing through that line, so we are changing the magnetic field that the line is emitting. So the question is how we are detecting the magnetic field. So we are using squids, which are quite sensitive to very small variation of the magnetic field. So we put a squid next to the line. So by measuring the magnetic field, which is changing with the radiation, we are able to detect the radiation coming from the universe. And this is the new instruments that is already installed in the radio telescope. And as okay, this is the description of the system. So we have the superconductive strip line, which is changing the inductance. Then we are using this squid, which is detecting the magnetic field. So once the magnetic field is flowing through the squid, the current in the squid is changing. So by measuring that current in the squid, then we are measuring the radiation. Of course, this is operating, I think this is operating at 150 millikelvin. And here, this is a picture of the inductors that we are using. This, I think, is this is a 1 micron 1 micron CMOS technology that we use for building these metallic superconductive stripes. And this is a photograph of the kit's array. And this is the system. So we have a feed horn that is filtering the radiation. So it's focusing all the radiation on top of the inductor. And then this is basically the system that we use for detecting radiation. And these are some of the pictures. This is the cryostat. Here you may see the mirrors that we use for focusing the radiation to the top of the system. And this is a picture of the array of superconductive detectors. And this is another picture here. And this is the whole system that we are using. And the size of this array, well, the size of each of these arrays is in the order of 1 millimeter. And so here you may see it's basically a system of 3 by 3 millimeter. The system, this is the inductor, this is the capacitor, and this is the line that we use for this resonator. And this is a picture of the transition temperature, which is below 1 Kelvin. Let me see, this is in I think this is millikelvin. This is somewhere in the range of 700 millikelvin. I think the image is out of focus. Can you read the scale? It's a little bit harder, right? Okay, anyway. Well, anyway, this is a sample of the encapsulated kit for the cryogenic operation. And so what is amazing is that you can build these devices using a standard CMOS facility, because this is a titanium aluminum metal, so that's a standard element metal that we use in CMOS technologies. And just by using these technologies, you are able to build these detectors that can watch what the universe is radiating out of. So we are detecting that. Okay. This is a view graph of, I can read it from here. So this is the transition temperature at which the material is becoming superconductive. And this is these are, in the x-axis we have different materials. So you see that the transition temperature is below 1 Kelvin. And what is interesting is that we have here titanium, aluminum here, which is compatible with CMOS technologies. But we have 3 different materials which are also CMOS compatible. So we can use a CMOS technology in order to build up these superconductive detectors. So the question is, can you read it? You can read it? Yes. Sorry. Okay. Even that I can read it. So this is aluminum. This is titanium. This is hafnium. Yeah. So hafnium is, yeah, hafnium. This one here. Beryllium. Beryllium, yes. Okay, anyway, these are the 3 different materials that we have in CMOS technologies and we can use for building superconductive materials. So, and what we have here is that The transition temperature is also a function of the material thicknesses. So if you make the material thinner, you will see that the transition temperature is going down. So we can play not only with the composition of the metal, but also with the thickness of the metal line in order to design what temperature we want to make for the transition. And so we can do that with a CMOS technology as well, so we can play with the thickness of the metal line in order to control the transition temperature. So, so the question is, can we use a regular CMOS circuit to integrate both the detector and the readout? Well, it's not easy. The thing is that if we use a squid as a readout technology for the superconductive detector, the problem with the superconductive detector is that the output resistance is 0. So you cannot use regular FET transistors in order to detect that. That's why we are using squids to detect the radiation from the superconductive detectors. And that means that we have to put everything together in a low temperature system. And okay. But there is something that we can do. If we want to put together the CMOS electronics together with the superconductive detector, that is called metallization as interposers. So I think that is something that is already known in the semiconductor industry, putting together two different substrates. And so you use silicon as an interposer, a metallization as an interposer. This is a picture that I took from this publication that came out just this year. So you can use different dyes. So you can connect these two different dyes through these metallic lines. Those metallic lines can be superconductive material, so you can connect them. So you can have in one side the detector systems, and the other side you can have the electronics. And I think this is a group from China, and this is a picture of same picture of the cryogenic interposer with aluminum from one side and titanium, the back metallization. So you put the sensors at one side and you put the electronics on the other side. So you can have everything together. As we know, the CMOS electronics can operate down to below 1 Kelvin. So this is an option if we want to put everything together. And the question is why we want to put everything together, the detectors and the electronics, the readout. Well, the answer is that we want to keep the noise as low as possible, so we can increase the sensibility. So this is one option, using this technique in order to interconnect the in one substrate, the readout electronics and the sensors. And this is something else. This is a window of this region here and also here. So we have a superconductive, I think this is titanium. Well, I can read it. Tantalum, yes. Tantalum and aluminum, yes. And this is a picture of the transition temperature, which is around 1 Kelvin. And this is a picture of the cryogenic chip sample, which was developed in order to test this interposer metallization. What is next? This is the next instrument, which we call Toltec. It's a 3-band image polarimeter for 1.1, 1.4, and 2 millimeter. This is already installed in the radio telescope. It has superconductive materials as detectors, and this is the numbers of pixels, more than 2,000. And this is a picture of the installation of the system. As you may see, it's not too big. It's like 1 meter. This is the cryogenic system, and all the instrumentation is inside of this box. And this is a picture of the array. It's an on-wafer more than 7,000 kinetic inductance detectors on a 6 inches silicon SOI wafer. And this is the 3-layer metallic system with a thickness of in the range of nanometers. And these are pictures of this system inside. And this is what I was telling you. If you wanna detect a picture of a very huge system like a galaxy, you need to use these devices, which are very tiny. So that's amazing, because in that way, we are just testing two theories. One is the relativity theory, which applies for big objects, and also the quantum theory, which is used to build up these devices. Okay, what else? This is amazing. This is a picture of the central Milky Way at 1.1 millimeter. It took, look at this, it took 10 hours with the Aztec system installed in the large millimeter telescope to take this picture. 10 hours using the Aztec system. If we improve the system and use superconductive detectors, this is what we see. But now we have the Toltec, and we may see different, it took like 15 minutes to take 3 colors, 3 different colors. So before that, it took 10 hours, 1 color. With Toltec, now we have 15 minutes, different colors, same central Milky Way. So yes, of course, when you are taking the pictures, you are moving the radio telescope. So you are taking different, you may say pictures, but you are collecting information, you are following the object. So the radio telescope is moving like this. It's following the object, and it's taking information. Yes. Mm-hmm. But it takes, in this case, it takes 10 hours. Mm-hmm. And this is the Toltec. So this morning, Adam was talking about using using qubits for processing information. So we were thinking in getting access to that computers in order to process the information, because this is taking 15 minutes using this large array of computers which are placed in UK and USA. And, but this is of great advantage, because we are going from 10 hours down to 15 minutes. And this is what is the next instrument, and this is being done in collaboration with the Arizona State University, Northwestern University, University of Massachusetts, Cardiff University, Michigan, INAOE in Mexico, and the National, what is the, yeah, standard, yes. And this is a picture of the system. You may see it takes 3 hours to close up this system, because you have to make vacuum in the system. So it's quite expensive in terms of time. And these are the optic devices that we use for the Toltec instrument. Those are operated at 4 Kelvin. And these optical devices were developed at UK. This is a picture again of how the mirrors are assembled, and here is the wafer where the arrays are located. And then we are not only working at with the radio telescope, we are also using optical telescopes. This is the optical telescope that we have in Mexico. And all the instrumentation has been designed and developed in Mexico. We built the complete telescope and the instrumentation. This is a picture of the electronics, and this is a picture of our optical shop where we are designing and building the mirrors that we need for this optical telescope, which is located at the Sonora State in Mexico. So those are some of the pictures that we are building in our lab. Those are optical components that we are shipping to different places in Spain for different optical detectors, telescopes. I think this is located in Spain. Also, this is in Spain. This is a picture of the Megara instrument at the Gran Telescopio de Canarias in Spain. So all the optical devices which are placed here were designed and built at our institute in Mexico. So in that way, we are not only building semiconductor detectors at very small dimension, but also the optical components which are used for this optical telescope. And perhaps you may think that these pieces are easy to build, but no, you need they need a very soft surface, well, the resolution is in the order of probably less than 1 micron, the roughness of the surface. So we use these these optical components and the bolometers not only for astronomy applications, but also for thermography. So these are some pictures of thermography that we are taking from a healthy patient. So when we have people with a disease like diabetes, so you may see that there is a presence of diabetes because the thermogram is changing. This is a normal thermogram with a healthy patient, and a non-healthy patient, this is the thermogram. So by using this bolometer technology that was initially designed for astronomy applications, so you can build medical instruments. So that's also another benefit of working with the astronomers by developing the scientific instruments. So you can use the technology not only for telescopes, but also for medical instruments. So this is one of the examples that we are now applying in Mexico. So the thermography for yes. Okay, so this is a picture of our lab. So this is one of the sections of our lab. We are using that for building transparent and flexible solar cells for mobile and wearable objects. So this is another benefit of developing a CMOS fabrication lab, initially built for building the scientific instruments for astronomy, later for medical applications, and now we are using this for solar cells as well. And this is the 0.8 micron CMOS fabrication laboratory. We have everything there. We have the ion implanter, diffusion, everything is there. And these are some of the pictures, some examples of different devices. These are electrostatically controlled micro mirrors. These are some RF circuits and micro electrodes for medical applications. And this is the one of the infrared bolometers made with silicon germanium, so that we use for the astronomy instruments. And this is another array of 4,800 pixels for a multi-spectral camera that we use in our lab. And this is a picture of the array. This is one single pixel, and this is already wire and bonded package device. So we use this in a system which is a 3D hyperspectral camera. So this camera is able to look at different conditions, not only in rainy conditions, smoke conditions. So it's a multi-spectral camera that is able to look at the different wavelengths under different conditions. The camera can see at the visible, infrared, fog, rain, and smoke. So that's for security applications. So that camera is also used for the calibrating the radio telescope, because if you go up and you need to calibrate the panels, you need to see through different conditions: fog, rain, ice, and even snow. So by using this camera, we are able to look at through different ambient conditions and calibrate the surface of the radio telescope. So that's why we developed this camera for different applications. So you can use this camera for your car. Oh, there is one pixel. There is only one pixel, so you are making a kind of a scanner. For breast, you can use also the bolometer for breast thermography. This is already built, and this is an example of 3 different conditions. So we use vertical polarization, and you may see these different kind of tumors. Horizontal polarization, and when you use circular polarization, you may distinguish between healthy and non-healthy breast. So we are just putting an optical filter on top of the bolometer, so we are able to detect positive or negative tumors for this thermography. And this is already in place, so we are already using this in different hospitals in Mexico just for testing. And this is another example of what we can do with a technology that was initially oriented for astronomy applications, and we are using this now for medical applications. Solar cells. So these are some pictures of a rigid solar cell, a flexible solar cell that we use for wearable devices, and transparent solar cells. These are nice because you can put it on top of if you have a crop, you can put the solar cells, this transparent solar cell on top, so you can produce energy and also protect the crop from infrared or ultraviolet radiation. And we are also able to produce light-emitting diodes using silicon and CMOS compatible technology. These are built on a temperature of 200 Celsius, so this is compatible with an integrated circuit process. This is a LED system. And we have also device characterization and reliability. This is our cryostat, where we are doing reliability down to 250 millikelvin, because we need to test the electronics that we are using for the radio telescopes. We have to test the reliability, so we have to make sure that the electronics is reliable enough to be operated under cryogenic conditions for a long time. And we are also involved in design of integrated circuits. And let's see, what time is it now? 1 hour. Okay. Let's see. So I will skip some of these slides. This is something that we are doing on reliability on 45 nanometer SOI technology. Perhaps this is familiar to you, Andy. So when we are doing DC stress on 45 nanometer CMOS technology, this is the regular reliability that it happens under DC stress. When you do RF stress, you will see that under certain bias conditions, the degradation is increasing with time, then you reach a maximum value, and then it's dropping down. So it looks like you are having a sort of, yes? So so the device is recovering. So we already, we were able to reproduce this in Mexico, in USA, and in India. So we make this reliability experiment on high frequency at different places, and we see that so this is a real effect. So there is a sort of a recovery when you stress the device In this case, I think we stress it at 28 gigahertz. So if you increase the frequency, then there is, you increase the recovery. So there is something which is going on there. Okay, so I will skip this as I, okay. So, so on Thursday, I will talk about performance and reliability at cryogenic temperatures. So I will talk that later this week. So finally, I want to come to the end of the presentations, that by using semi and superconductors and quantum electronics, we are able to detect different chemical compositions from the universe. This is the picture that I already showed, where we can see different molecules detected at the universe, and which are telling us how the origin, how the universe is the origin and the evolution. So for that, we just manipulate the structure of these devices. We use device fabrication, and so we can go down to quantum computing by using superconductor devices. And okay, I will skip this. These are some of tests that we have been doing on the 14 nanometer FinFETs, just to be sure that we can implement the electronics using advanced CMOS technologies for these astronomy applications. I will skip this. Marcelo, you were asking about the system. This is an on-chip self-heating sensor that we use a system in Germany. This is a cryostat, where you can have the needles and you can make the test on silicon. This is down to 6 Kelvin, I guess. Okay, so I'm closing my presentation. This has been a journey from the astronomical universe down to the atomic scale. So we were able to build the image of the black hole by using devices which has a scale of micron and nanometer size. Well, with this I will end my presentation. So, muito obrigado, thanks, gracias.
What a journey.
Yes, yeah.
Well, people, we have a couple of minutes of questions. Patricia, starting with you.
If you want to visit the telescope, you are welcome. It takes probably some, if you have to take a plane with a connection in Panama, it takes like 20 hours from Rio to Puebla city. But okay, you are welcome anyway.
Oh, thank you. For the black hole detection that you showed, how can you know precisely the depths where it's coming from? Because, I mean, you're looking at a certain place, but how do you know the signals of all these components that you detect? How can you know exactly where it's coming from, I mean, depth-wise?
Well, there is a calibration system. So every one of those 8 radio telescopes, they have a calibration system. They have an electronic system which is calibrating the sensors. So by taking the measurements from different places on the Earth, then you make an extrapolation, and because of those 8 radio telescopes are synchronized in time, then you can define the distance. Remember, what we are testing with these radio telescopes is the theory of relativity. Mm-hmm. So you have different references, you have different positions, and you have one reference, so you can calculate the distance.
Thank you.
In some of your technological slides you demonstrated the use of SOI wafers. Is there any special reason for selecting SOI instead of regular bulk CMOS?
Sorry, what?
In one of your slides, you
Yes.
mentioned you were using 6-inch SOI technology.
Okay.
And is there any special reason for making an option for SOI instead of regular bulk?
Well, SOI, it's because we only need the SOI wafer as a mechanical substrate. So we need an insulator layer, and then we need the silicon on top of it as a mechanical substrate for the superconductive inductors. That's the reason that we use the SOI wafer. But we can use 4 inches, 6 inches, and I think 6 inches is the standard now for building this array of superconductive devices. But there is no special reason behind the SOI that we need as a mechanical substrate for the array of sensors.
Ah, okay.
Yes. Mm-hmm.
So you're saying that the silicon wafer would be the same mechanical substrate. It doesn't have to be SOI.
Mm-hmm. Yes.
So it just happens to be on your shelf,
Mhm.
and you pick it because you have it.
Yes.
And you're used to using SOI.
Mm-hmm.
And
Yes.
somebody who used SOI before likes to use SOI again.
Mhm.
So it's a conservative approach because it works.
Yes.
Any other questions, please?
One comment I want to make is that we have not many customers because there are only a few radio telescopes in the world, and those scientific instruments are not built every day, so they are requested every 5 or 3 years. So they are just building the next generation of the scientific instruments. Yes. Yeah, but look at the application. In this case, we are not working at high frequencies. Yes. Mm-hmm. Yeah. But consider that we are fabricating these devices once. It's not the cost is not a matter in this. Yeah. Mm-hmm. Yeah. So yes, that's right. And so you don't need any complex wafers for building these devices, but there is an additional benefit because by developing this technology, you can also develop instruments for security applications. Because you can use these devices in order to look through the body and find metallic objects like weapons. But I don't want to comment on that because so. Mhm. Yeah. Yeah. The only issue with these applications is that you need to cool down the devices below 1 Kelvin. So if you can imagine having this big cryostat. Yeah. But anyway.
Okay. Any other comment or question? No? So let's thank Edmundo again.
Thank you.
So we are about the break. There are just 5 minutes for the coffee break. It will be served somewhere else. And then at about 3:40, we are back for the last presentation, right? Which will be given by Dr. Andreas Keller. See you there.